This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Good evening and welcome. My name is Nigella Hilgarth and I'm the Executive Director of the Birch Aquarium at Scripps Institution of Oceanography. And it's my great pleasure to introduce tonight's Perspectives on Ocean Science lecture series. It's actually the Jeffrey B. Graham Perspectives on Ocean Science lecture series. And it's wonderful to have Jeff with us tonight. And I'm now going to introduce tonight's speaker, Dr. Sarah Gilley. Professor Gilley earned a bachelor's degree in physics at Yale and a PhD in physical oceanography from the Massachusetts Institute of Technology and Woods Hole Oceanographic Institution. They have a joint program. Then she did postdoctoral research here at Scripps Institution of Oceanography and also at the University of East Anglia in Britain. And then she was a faculty member at the University of California at Irvine. And then she joined the UCSD faculty in July 2000, and she now holds a joint appointment here at Scripps Institution of Oceanography and also in the Department of Mechanical and Aerospace Engineering. And Dr. Gilley's research focuses on ocean dynamics and global climate, especially in the Southern Ocean. And that's a really amazing area where you get the Pacific, the Atlantic, and the Indian Oceans all converging, making some very exciting and interesting and important research. So please join me tonight in welcoming Sarah. Her presentation is called Probing Long-Term Temperature Change in the Southern Ocean.
I'm going to talk today about the long-term climate change in the Southern Ocean. And just to orient you, I've put up this figure here. This is showing the Southern Ocean. It's the part of the ocean that is south of 30 degrees south or 35 degrees south. And as Nigella said, it's interesting from an oceanographic standpoint because it's the connection between the Atlantic, the Indian, and the Pacific Oceans. And also because it's sort of a barrier. It's the division between the subtropics or the tropics up here and Antarctica. So when oceanographers think about the Southern Ocean, we think about several features. It has multiple jet-like currents, which together comprise what's called the Antarctic Circumpolar Current, which carries water around Antarctica in this direction, clockwise in this figure. And the transport of that is roughly comparable to what the Gulf Stream takes. So it's quite a big current. Now, everybody at Scripps feels like if we talk about climate, we have to show the Keeling curve. So I thought I'd get that out of the way right away. I'm sure if you've been to these talks before, I'm sure you've seen this figure before, but I'm compelled to talk about it too. Of course, this stems from the work of Dave Keeling, who was a scientist here, and starting in 1957, he began making measurements in Hawaii of carbon dioxide in the atmosphere. And what this 50-year-long record now shows is this amazing increase in carbon dioxide in the atmosphere because of human activities. The increase is strictly because of human activities. What you see is the oscillations which go with the annual cycle of plants growing and decaying on land in the northern hemisphere, so there's a constant oscillation. But the big change can only be explained by humans burning fossil fuel. So we've seen this steady increase in carbon dioxide, and the natural question is not just whether this is real, we're very certain of that, but what it means. So I want to give you a quick tutorial about how we as climate scientists think about the climate system, and then talk about what the implications are for this rising carbon dioxide in the atmosphere. So this is going to be a very broad brush view of how the climate system works. But in essence, we think of the climate system as, here's the Earth, a nice blue planet. Essentially, all the energy that comes into the Earth comes from the sun. So here's the sun. The scales are slightly distorted here to fit everything on the screen. And what's important are two things here. First of all, the sun's energy comes predominantly down in the tropics, in the equator. So there's lots of sunlight at the equator. And that energy that comes in from the sun doesn't just come into Earth. It's not a one-way interaction. The energy comes in, and it is balanced by equivalent energy going out. So you see this long wave or infrared radiation going out from the Earth. And as it happens, that doesn't happen right where the energy comes in. It's spread much more uniformly. So there has to be transport in the ocean and atmosphere to move that energy from the sun from the places where it comes in to the broader region where it comes out. Now, what makes this this whole idea that the heat actually stays on the planet possible is that we have an atmosphere. So here's a schematic then showing our atmosphere, which consists of a whole lot of greenhouse gases, among them water, carbon dioxide, which is increasing, methane, essentially natural gas. And what these greenhouse gases do is to trap some of that heat that's going out, so that instead of just radiating straight out into space, it stays in the atmosphere. The heat stays around the Earth for a little bit of time. And you can think of it as being like being in your bed on a cold night and putting on an extra blanket. You're just trapping more heat around you. Or here's a different analogy. We'll think of this as something like stream flow. So we have a stream here. You have water coming down, and it's a pretty constant flow of stream coming in at the top. So you could think of that as being like the energy from the sun coming in and going out of this picture at the bottom. So that could be like the energy from the Earth going back out into space. Now, our atmosphere acts sort of like a dam. So we have energy that comes in, still the same rate, but it's trapped in a reservoir. This heat that keeps this planet habitable, that makes it possible for us to live here. So we have a certain amount of heat that's held to Earth by our atmosphere, which is full of greenhouse gases. And then the water spills over the dam. It's basically allowing the same stream flow going in and out of this, just with a reservoir of heat in the middle. Now, what this increase of CO2 in the atmosphere has done is essentially to raise the height of the dam. So now we have a bigger reservoir. We have a warmer, lower atmosphere. The planet has gotten warmer, but we still have a balance between the heat coming into the Earth from the sun and the heat going out at the bottom. Aside from this minor thing that we had to fill the reservoir, we continue to slightly fill the reservoir all the time. So we're expecting that with increased greenhouse gases, we would expect to see a warmer planet. And just to give you a perspective on this, I thought I'd give you a few numbers here. The atmosphere is pretty tall. Stretches 100 kilometers or more into space. But it's not very dense. And if anybody scuba dives, you know that the entire atmosphere has a mass, a density, or a weight that's equivalent to the top 10 meters of the ocean. And the ocean is, in fact, about 4 kilometers deep. So we've got about 400 atmospheres of mass, of weight, at the bottom of the ocean. The ocean is just massively more stuff than the atmosphere. And on top of that, the heat capacity of the ocean, or the ability of the ocean to absorb heat, is somewhat different from that of the atmosphere. So in fact, the top 2.5 meters of the ocean has the heat capacity of the entire atmosphere. That means that if I warm the entire atmosphere by 1 degree Celsius or 1 degree Fahrenheit, that would be equivalent to warming the top 2.5 meters, something about the height of this room, in the ocean by 1 degree Celsius or 1 degree Fahrenheit, whichever units you want. So we have the potential to put a lot of heat in the ocean. And the question you might ask is that really happening? So I'm going to show you a figure here from a study done by some people at the National Ocean Data Center, who made an effort to go through all of the historic oceanographic data that were available and to assess how much the ocean the heat in the ocean has changed over time. So here we're looking at a change from the mid-1950s up to about 2005. And they've separated this here into the southern hemisphere, the northern hemisphere, and the world ocean. And this is in units that are a little funny. This is looking at heat content in units of 10 to the 22nd joules. So this is over the top 700 meters of the ocean. But you probably have, it's hard to get a handle on what that is. That's essentially equivalent to warming the top 700 meters of the ocean by 1/10 of a degree Celsius, or 2/10 of a degree Fahrenheit. If your bathtub warmed by 1/10 of a degree Celsius, you'd never notice. But this is spread over 700 meters of ocean, so it's actually quite a bit. Warming the upper ocean by this amount, by something like 4 times 10 to the 22nd joules for the southern hemisphere, is roughly equivalent to, well, that's over 50 years, so that's equivalent to warming the southern hemisphere ocean by 8 times 10 to the 20th joules per year. And remarkably, that is nearly double our current energy usage, the energy usage of all of the people on this planet. And that was only the southern hemisphere. We had in the northern hemisphere. Essentially, the warming that has occurred in the ocean over the last 50 years is about 4 times greater. It involves about 4 times more energy than the amount of energy we've burned using fossil fuel in that time. And it's quite a bit more than that, because I'm talking about the current rate that we're using energy. Just to put a handle, another colleague puts it a different way. He says this warming of the upper ocean, it's about like 2 billion Hiroshima bombs. Very sobering statistic. And then the person who told me this said, and Hiroshima wasn't really a very big bomb. But now, so we've seen all this rather remarkable warming in the ocean, and I think if you've been following the news in the last 6 or 8 months, there's sort of this disconnect between the warming that appears in scientific papers and the sort of thing that I look at, and what came out of in the media excitement at the time of the Copenhagen negotiations back in December, when, as you may recall, there was this climate gate thing. Some people at the Climate Research Unit at the University of East Anglia had their computers hacked into, their email was stolen, and somebody culled through thousands of lines of email and cherry-picked some statements that made it look like climate scientists were all corrupt fraudsters trying to do self-aggrandizing science. And so this political cartoon appeared in the Denver Post. There's a polar bear here standing on a very small iceberg saying, "Global warming is a hoax, brace for ice cap refreeze," while his friends are here possibly drowning and certainly looking very unhappy in the water, and there's not much ice around. So you may wonder then, how come there's this ClimateGate thing saying there can't possibly be global warming, it's all a fraud, and I'm sitting here telling you, well, here's the research that we all do. So I really wanted to give you today a very personal perspective on, from the trenches, what we as researchers look at when we think about global change. So it's going to be maybe more attuned to the difficulties we face doing research rather than the self-aggrandizing questions of warming. But what I wanted to point out here is, first of all, if you look at this figure I showed before, you can see there are uncertainties on this, and that's one of the things that researchers really like to think about. We don't like just numbers, we like to know how much certainty or uncertainty they have associated with them. And the uncertainties in the southern hemisphere, these vertical lines, are larger than the uncertainties in the northern hemisphere because there's less data available in the southern hemisphere. And what that means when you add these two hemispheres together is that the uncertainties are large for the world ocean. So the questions I want to address today are really threefold. First of all, given all these large uncertainties, do we have any chance at refining our estimates of heat content change? And then, more broadly, can we drive at the questions that really excite scientists, not just is it warming, but what explains the warming? And what does ocean warming imply for the climate system? What are the broader implications of these patterns that we see in the ocean? So I want to come back to the Southern Ocean. This shows you And the Southern Ocean is problematic because it's a place that hasn't really been sampled. This is showing you all of the data that were collected from the 1930s up to 1990. And what you can see is there are parts of the Southern Ocean, for example, here in the Atlantic Ocean near Drake Passage, where there's been pretty steady sampling through many decades. You can see lots of different colored dots and lots of dots. But there are other places that were really not sampled or barely sampled at all in this 6-decade time period. So there really is very little data available. What happened in the 1990s is we had a real expansion in our ability to collect data. So traditionally, data had been collected from ships. This is a CTD rosette with bottles that took water samples, and there's a CTD, a conductivity temperature depth probe, mounted in the middle of this that is going to measure temperature and salinity as this is lowered from the ship down through the water column. Now that takes about 4 hours to do from top to bottom of the ocean, and then some time to move the ship to the next station. So it's very time consuming. But we've also had new data available that have really expanded our ability to see what's happening in the ocean. So expendable bathythermographs were launched much more extensively starting in the 90s. And I think the real innovation was something that came out of Scripps, what were initially called Alice floats, and then they started profiling. So they're profiling Alice floats. That's this guy here. These independent, sort of autonomous floats, which have now transformed into Argo floats. And what they basically do is that they're launched off a ship, and they transmit their position to a satellite, and then they go down to about 1,000 meters depth, and they drift along through the ocean for a week or 10 days of pre-programmed time, and then they rise up to the ocean surface, and as they rise, they collect a profile of temperature and salinity. So we get measurements of the water column with each of these profiles. And when they reach the surface, they send their data back via satellite to shore so that we have a continuous record of what the ocean temperature is doing. Now, we have no control over where these floats go, but they're making a lot of measurements, and that's turned out to be an enormous boon to our ability to measure the ocean. So the floats are designed to be relatively easy to launch. You can see they're about the height of a not too tall person, and 2 people are pretty easily able to get this over the shore, over the side of the ship and into the ocean so that it can start operations. This is launched in the Southern Ocean, Indian Ocean sector. So you can see that everybody's bundled up for the cold weather. And so just from the 1990s, we got an amazing array of observations. I showed you the rather sparse records that came out of 6 decades of shipboard observations. These are the measurements that we got from floats just in the 1990s alone. And this is showing, here there are little arrows showing the paths that each of these floats took as they moved from each place they profiled. So you can see each float keeps a constant color, and you can see they tended to move around following the Antarctic circumpolar current, and they moved quite a distance over that time period and gave us really very complete coverage of the Antarctic circumpolar current. They tended not to get out of the current, so there's still big data gaps north of the circumpolar current because it's hard to get floats there if you don't send a ship, and the floats aren't being propelled there by a current. So when I started looking at the data, I asked really basic questions, and this is where I really want to give you sort of the personal view of what my trajectory through this data. But the first thing I did was to ask, are these float data any good? And so I pulled out atlas data that had been mapped by another group showing temperatures in the ocean from historical data. And this is this map here. It shows cold temperatures near Antarctica, warmer temperatures to the north. And then I mapped in the same way the data that came from the floats from the 1990s. And I was really pleased to see that, in essence, it was very similar. Now, the floats were not set up to go under ice. If you have a float and it has an antenna on top and it comes up under an ice shelf, the antenna dies and you lose the float. So they were not launched under ice. So, of course, there's a data gap in the south, and I wasn't concerned about that. But what I looked at was where they do compare, I saw the same pattern of cold temperatures in the south, warmer in the north. It was warmer near Australia, colder near South America, across the Pacific Ocean. So these patterns looked really similar, and I thought, this is great. These are really looking like a great data source. They don't seem to have obvious problems. And then I looked at the difference between these 2 maps. And this was rather remarkable because what it showed was a very significant difference between these two, consistent with the floats, the data from the 1990s being a lot warmer than the data from the previous decades, warmer by 0.2 degrees Celsius or more. And so I thought, okay, well, there are a lot of explanations for this, and since scientists tend to be skeptical, and I'm happy to be skeptical with everybody else, my initial inclination was that we had a data calibration problem, or that we were having biases because we weren't getting under the ice and we were missampling the ocean, or that there were mapping problems. But the great thing about Scripps is that we have lots of expertise, and so I went around and talked to the people who developed the floats and said, do you think it's a calibration problem? And we thought about it hard and decided that no, there was no way that a calibration problem, even if there were calibration issues with the floats, there was no way that we could get a consistent 0.2 or even 0.5 degree difference just from a calibration problem. And then I was concerned about mapping issues, and I thought, okay, well, I also, of course, talked to people who'd collected data in the 50s and 60s and said, how good were your measurements? And I got assessments from them about what they thought were really reliable and what they thought the problems were with the instrumentation that had been used early on in the record. And then, so I was then concerned about mapping issues, and I said, okay, instead of all this fancy mapping, let me do the simplest possible comparison I can do. And so I'm going to show you results from that. What I've done is to say, okay, for each 1990s observation, I'm going to use those as a reference, I'm just going to look for data that I can pair with it, data collected geographically within 110 kilometers, so that's equivalent to a circle of about 1 degree latitude, or 220 kilometers, a 2 degree latitude equivalent circle. And I'm going to just pair up all these observations. So for this float, you can see there'd be 2 pairs within the 110 kilometer radius and a total of 6 within the 220 kilometer radius. I'm going to look at the temperature differences between these. So if I do that, this is looking just at the depth of the float's drift, and we're looking at about 900 meters depth. And I'm comparing the temperature from shipboard data to the float temperatures. And what you see is a very steady trend that's consistent with a progressive warming of the Southern Ocean. So what we see is, so the error bar is large in the, for the 1990s because not all the data were available at the time I did this. The error bar is very large, the uncertainty is very large in the 1940s because there was a world war going on, and I think the Navy was, if they collected data, they were supposed to archive it, and they archived it in a way that nobody's been able to locate. But overall, from the 1930s, we don't know too much about, there really weren't very many observations, but from the 1950s up through the 80s, you see this very steady warming, and remarkably, this is equivalent to about 0.2 degrees Celsius warming at this depth, at 900 meters depth. So that's amazing. It is roughly equivalent to the warming that's seen in the atmosphere over the same time period, and it's double the warming that I told you that other study had shown, the Levitas et al. Study had shown over the same time period. So we've got this suggestion that there could be really rapid warming going on at 900 meters depth in the Southern Ocean. And in fact, in general, this was showing about that the 1990s data were warmer than all of the historic data by, on average, about 0.1 degree Celsius. So where did this warming occur? Well, just looking at these pairs here, we're looking at warming, and this is a funny way to present it because we're looking at a rate of change. This is in degrees Celsius per year, and it's been averaged. But the message is pretty clear. If the ocean has been warming over this time period, it's shown in yellow and red. If it's been cooling, it's blue. And what you see is this whole band that corresponds to the Antarctic circumpolar current, this region going around Antarctica, shows evidence of having warmed over this 5 or 6 decade time period. In contrast to the north, there's some evidence of cooling. So we have a real contrast here where it looks like the Antarctic circumpolar current has warmed pretty substantially over this time period. Now, from that, it made sense to actually do something that we could compare more completely with the previous studies. And so here I've gone back and looked at the entire southern hemisphere so that we can compare with the other study I showed you earlier. So here are 1990s observations. They come from a whole bunch of different sources, floats, profiling floats and CTD data and expendable bathythermographs and bottle data. And this is all the data that was collected in all the other decades. And if you ignore the red dots, which are from the past decade, you can see that there's some pretty sparse areas, sparse coverage through much of the southern hemisphere. But if we put this all together, what we can get is a picture of how the southern hemisphere ocean has changed over time. So this is showing temperature differences. We're looking as a function of depth from the ocean surface down to 900 meters depth. And we're looking at temperature change in degrees Celsius. And what you see is that relative to the 1990s, so the 1990s relative to themselves are the same, so that's a 0. But relative to the 1990s, the ocean was much colder in the past. So we see this progressive warming from the 30s in purple to the 40s in dark blue, the 50s in light blue, the 60s in green. The 70s are this sort of chartreuse, the 80s are this gold, and then the last decade is red. It's showing an increased warming. So there's this very steady progression of temperature in the ocean over this entire time period. And it's a warming that's occurred from the surface pretty much all the way down to the bottom of the depth range that we're able to resolve. Now, there are real issues in this, and I wanted to try and give you some picture of what we struggle with in trying to look at this. So the real issue is, of course, that we don't have a lot of data. There's this, somehow people don't like going into a part of the ocean called the roaring 40s or the howling 50s and collecting really dense observations. And if they don't like doing it in the summer, they really don't like doing it in the winter. So there's also a strong seasonal bias in the historic observations. The floats don't have that problem. They work year-round. But we end up with large areas of the ocean that have no data. And so the question is, if you have a sampling pattern that looks something like this with a big hole, how do you tell what the real trend in ocean temperatures is over that time? So there are a bunch of ways we deal with it, and I thought I'd sort of trace out some of the strategies. One way to do it is to say, well, we're just going to break the ocean into regions, and we'll look at a trend in each of these regions. And if we have a region with no data, we'll assume there's no trend there. So that means that if you have no data anywhere, you'd assume that the ocean had never changed. It's a very compact statistical assumption. Another possibility is to break the ocean into very large boxes, make sure there's data in every box, and average the temperature trends in those boxes. Maybe a better strategy is to say, well, in fact, the ocean has stronger variations as a function of latitude, so going from north to south, than it does in boxes. So how about if we average in latitudinal bands? So we could do something like that. Or we might say, well, in fact, the ocean has these currents that go all over the place, so why don't we follow the path of the currents and average in regions that are defined by the flow of the ocean currents. So we'll have a dynamical regime that defines which of these blue dots we average together when we try and figure out how ocean temperatures are changing over time. So in trying to assess these changes in the ocean, naturally, part of being a skeptical scientist is that you try everything. So I tried them all. So here I'm showing you results that come from each of these different strategies. So the blue line is the line corresponding to the results I showed you before from the Levitas et al. Study, showing their temperature trend. And then I've got these other lines. There's some gaps where there aren't adequate data, but you see these trends for averaging in red is averaging in dynamical regimes. The gold line, which is sort of hidden, is averaging in latitudinal bands. If I just average everything together as if the whole ocean is one bin, I get this enormous warming trend corresponding to this sort of funny olive green line here. The green line, the bright green line here corresponds to averaging in 5 degree by 5 degree bins with some weighting to account for missing data. And it turns out that the only version I get that matches the previously published studies is the one where I assume that if there are no data available, there's no trend. So that turns out to be the most conservative possible estimate of global ocean warming. It would be easy to conclude that over the 7 or 8 decades since the 1930s, ocean heat content has increased in the southern hemisphere, not just by 4 times 10 to the 22nd joules, which is what I showed you before, but by more like 25 times 10 to the 22nd joules, by quite a bit more than some other studies have shown. And so you might say, okay, so this is disconcerting, because on the one hand, you have these people telling you that climate researchers are all overestimating things and trying to create larger trends than are really occurring. And here I'm telling you that I try every possible strategy, and the only way I can get a trend as small as what's in the published literature is to assume that anywhere there are no data, there's no trend. So that to me says that the published literature in many cases is, as you'd expect from very cautious scientists, is more cautious than might be even justified by statistical assumptions. This is not uncommon in climate science, actually, and I thought I'd give you a little entirely different example just to back that point up. This is from the Copenhagen diagnosis, which was a study put out to, or a compendium of scientific results put out at the time of the Copenhagen negotiations to try and show climate science advances since 2007, since the last IPCC report came out. And here, this study shows that if you track sea level rise globally, you can see that global sea level has risen since the 1970s, following tide gauge data. Since 1992, there's been very good satellite data showing a very steady rise in sea level. And the point here is that we have the observations that show one set of values of sea level rise. The models that are used to predict sea level rise show an envelope of different values that spans this region. And so if this is the envelope, you might have expected that the observed sea level should run right up through the middle of that envelope. But no, the observations are at the very top. The predictions, the projections from the climate models are really too conservative relative to what we observe. So we struggle then with maybe being too cautious in explaining the results of climate research. So I want to move on from here and ask some of the more arcane questions that we consume ourselves with when we study the climate system. One of them is to ask, well, really, where is this warming taking place? And so I pointed out to you before that we often like to think of the ocean in terms of dynamical regimes following the flow of the currents. And so here what I'm going to do is follow what's called dynamic height, following around Antarctica. And so you can think of this as showing the height of the ocean surface, which is about a meter higher on the north than it is on the south, if you could get rid of all the waves and everything else that complicates things. So we're going to look at these contours that correspond to this range from about 0.6 to 1.2. So this light blue range going all the way around Antarctica. And what I'm going to do then is average the observed ocean warming from my analysis as a function of depth and these height contours. And what you see then is that the warming trend, so we're looking at a rate of ocean warming in degrees Celsius per year. And what you see is that if we look in the 0.6 to 1.2 range that corresponds with following the circumpolar current through its convoluted path, we see very significant top to bottom warming. If we look to the north over here, we don't see as clear a trend. And you'll also see that at the ocean surface, in the Southern Ocean, we see some evidence for cooling. I'm not convinced that's not just an artifact of this habit people have of measuring the ocean only in the summer. So although I've tried to correct for it, I may have missed part of that. But there are other possibilities that may also explain it. So this is a really interesting pattern of warming, and I think the question that we ask then is, well, why? What controls this pattern of warming? So if I'm thinking about what makes the ocean change, the ocean has warmed up over time, so there has to have been heat input from somewhere. And if we're thinking just about the Southern Ocean, the heat could come from the atmosphere, or it could come from within the ocean. And if it comes from within the ocean, it could come from transient effects from eddies or the weather in the ocean. So things that move heat back and forth without really moving anything permanently. Or it could come you could see an effective warming of the ocean by taking the entire Antarctic circumpolar current, all its jet-like structures, and moving them all southward. So moving a fixed temperature structure southward on a permanent basis. So I guess we want to try and figure out if we can get either of those to be a plausible explanation for what we observe. So we've got two possibilities, really. We can either warm the ocean by having heat diffuse down from the atmosphere, and that would give us a trend. Again, we're looking at as a function of dynamic height here, but that would give us a trend that looks something like this, with warmer water, greater warming, I guess, near the ocean surface and less warming at depth. Or we could imagine taking the Antarctic circumpolar current, taking the whole temperature structure of the Southern Ocean and moving it poleward towards Antarctica. And that would give us a pattern sort of like this. Now, if you look at these two patterns, this one doesn't look at all like what I showed you before. Well, this one looks a bit, and I'll just line them up here. So this is the predicted trend if you move the current, and this is the observed trend. And what you see is they don't look particularly similar north of the Antarctic circumpolar current over here, but in this region corresponding to the circumpolar current, these are actually a pretty good match. And below 200 meters, you're able to explain about 95% of this observed trend as simply a result of moving the Antarctic circumpolar current poleward at a rate of about 1 degree in latitude per 35 years. Now, you might think that's absolutely implausible, but it turns out that the winds appear to have changed comparably over this time period. And so there's been an intensification of winds in the Southern Ocean and also a poleward shift in the winds due to a combination of the ozone hole and greenhouse warming over this time period. So we have this explanation that still remains to be fully tested, that the ocean has warmed, that we see it as warming because the Antarctic circumpolar current has been able to migrate poleward over this time period. So now, the other question you might ask is, did humans really cause this warming? And so I thought I'd show you some results from modeling studies that try and assess this. This is work from a climate model put out by the Hadley Center in Britain, where they tried to say, okay, if we have one computer simulation of the climate system that has no human-based warming of the ocean and one that has warming due to increased carbon dioxide, how do they differ? Where would we first be able to tell that there was warming due to human activities? So they've looked here at the Arctic and Atlantic Ocean. The shaded areas show where there's significant warming. And you see in the Arctic and Atlantic, there's a large shaded area in the deep ocean, but there's really nothing detectable in the upper ocean, in the surface. Here's the Pacific Ocean. There's some patches where they'd expect detectable warming after about 35 years. In the mid-depth, nothing at the surface. And then here's the Indian plus Southern Ocean, and you see this very large, distinct region of rapid response to greenhouse warming in the Southern Ocean that is essentially top to bottom, and that corresponds to this region of, well, tilted contours here. So we're looking from 30 north to 90 south, and from the surface down to 1,500 meters, and this is essentially this region of tilted contours is the region that would be the Antarctic circumpolar current in this particular model. So what this model is predicting is intense warming should be readily observable in the Antarctic circumpolar current. Now that's just one model, and there are dozens of models being run globally. In fact, if you look at this particular issue in an ensemble of 20 climate models, they pretty much all show the same thing, that they expect to see an intensification of the winds in response to greenhouse gas increases in the atmosphere, and as a result of that, a shift in the position of the Antarctic circumpolar current and warming of the ocean. So this pattern is very typical of models. And there's still issues that we need to resolve. The models don't always resolve all the small-scale weather-like eddy effects in the ocean, and we have to ask what the role of those effects is in explaining warming. But this is certainly very consistent with the model that we get. So then there's some open questions that we ask when we try and want to understand what this all means for the climate system. So one question is, okay, if we warm the ocean, how does that change carbon dioxide uptake by the ocean? As you probably have heard if you've been to these lectures before, carbon dioxide is emitted into the atmosphere, but the vast majority of the carbon dioxide that goes into the atmosphere doesn't actually stay in the atmosphere. Much of it goes into the ocean. And in fact, much of the carbon uptake in the ocean is concentrated in the Southern Ocean. Here we're looking at this purple line, shows carbon uptake in the ocean. This is from a computer simulation. We're looking from 90 south to 90 north, but what you see is this really intense peak of carbon uptake by the ocean concentrated right in the core of the Southern Ocean. That's not actually where the carbon stays in the ocean. The storage is slightly further north and spread out more through the ocean, so it's transported through the ocean. But there's this uptake. Now, so if we change the winds, if we make the ocean warmer, carbon dioxide is more soluble in cold water than in warm water, so that might make it harder for the ocean to take up carbon dioxide. But changes in winds and changes of the latitude of the wind may also affect the uptake of carbon dioxide in the ocean. So there are real questions about how much carbon dioxide the ocean would continue to take up if we have a change in the temperature structure of the Southern Ocean. And that's another question that remains an area for active research. I think the other question that is a real puzzle for many of us is, what does all this warm water mean for the stability of ice around Antarctica? So here I'm showing you a picture showing the amazing retreat of the Larsen B ice shelf, which collapsed in 2002. So in January, the ice front was here following this blue line, and by March of the same year, it had retreated back to this red line. So there was a very catastrophic collapse of the ice shelf, the Larsen B ice shelf. Now the question that we can ask is, if we have warm water in the Antarctic circumpolar current, comparatively warm water, that is suddenly, as a result of this shift in currents, is brought closer to the Antarctic continent, is that actually contributing to melting of the under edge of this ice? Is that helping to destabilize this ice? And ultimately, if we destabilize this ice, if this ice shelf collapses, then the concern is that that makes it easier for ice to slough off the Antarctic continent. And if you remove ice from the continent, it goes into the ocean, that raises sea level, and we have to worry about what the implications are for global sea level rise. So there are real concerns in understanding this and trying to pick apart exactly what's going on. So I want to summarize quickly here. I've shown you results that indicate the Southern Ocean has warmed significantly over the last 50 years, and the warming is really concentrated in the Antarctic circumpolar current. I've shown you that there's mid-depth warming of about almost 0.2 degrees Celsius, about 0.3 degrees Fahrenheit from the 1950s to the 1990s, and that really warming is evident at all depths and throughout the Antarctic circumpolar current region. And that this warming could imply a migration of the Antarctic circumpolar current towards Antarctica, perhaps driven by changes in the latitude of the wind forcing. I hope that in talking about this, I've also conveyed to you some of the complexities of what we worry about doing climate research, that we worry much more about uncertainties and mechanisms driving this and implications than about a single number that shows that warming occurs or doesn't occur. So, thank you. This was a big puzzle. So what you're pointing out is that there's this steady rise and then a drop and then a continued rise. And they all show it. And so people puzzled over this for a long time. And everybody repeated the analysis. Other people got the same result. It seems to have turned out that there were changes in the instrumentation people were using. And there were some quality control issues that were not quite wrapped up in that. Those have been resolved now, and I don't have an equivalent figure that fully corrects this. So, if you correct it, it shows a much more steady rise. Yeah, it's a much better figure now. I just didn't manage to extract the right comparison. It hasn't been. You think that I should be able to do that, but it's not always the case that somebody has published exactly what I want. So the question is, if you look at this particular picture, what you see is that there's warming around Antarctica, but there's evidence for cooling to the north. And so it's easy to try and explain why there's warming. It's much harder to come up with a simple explanation for the cooling, but I think the best explanations have to do with the fact that the ocean circulation is a 3D circulation, and an intensification of the winds would lead to an increased upwelling of cold deep water, which could actually increase the cooling at this particular depth in this region. Overall, we do see a warming, at least at this latitude, in the global ocean. So you're asking about different expectations for different parts of the ocean to have cooled or warmed, as I was talking about with this figure, and what that might have to do with larger scale, long-term deep ocean circulation. And you asked about an 1,800-year cycle. I think one of the most remarkable things we've learned in recent years is that the deep ocean circulation may be a lot faster than we used to think. So we actually see, what I haven't shown here, but we actually do see evidence of deep ocean warming over, that's clear evidence of anthropogenic warming penetrating into the deep ocean over just a few decades of time scale. But yes, the question you're asking, if we talk about this as part of the three-dimensional circulation, that's really part of what we talk about as the meridional overturning circulation, or sometimes people talk about it as a global conveyor belt circulation. So I hope I've managed to answer your question. So this is a question about why we see this big pink spike in the Southern Ocean for carbon uptake and almost nothing in the Arctic. And that really has to do with the differences, the substantial differences in the circulation in the Southern Ocean versus the Arctic. So the Southern Ocean is characterized by this very strong current, the Antarctic Circumpolar Current, which is tied into the global circulation, and it provides a pathway by which carbon dioxide and other gases can easily enter the atmosphere, transfer from the atmosphere into the ocean. Those pathways are not as readily available in the Arctic. So there's some pathways in the Labrador Sea. We see some evidence for deep water formation or interactions, but it's simply not able to take up as much carbon dioxide as quickly. Yes, the question is the Antarctic Circumpolar Current controlled by the Coriolis effect, and it is, as are most major currents in the ocean. In the northern hemisphere, there's more land in the way, so there's less ocean. But the difference in land and ocean is not equivalent to the difference between this peak and this peak. So there are other things that are affecting it as well. Is the high carbon uptake related to the Southern Ocean being an area of rapid warming? They are related, but I think they're indirect effect. They're both results of the same effect. And I think the leading effect is simply that what we think of is that the mid-depth ocean in the Southern Ocean has a direct connection to the ocean surface. There are layers of the ocean functions on density surfaces, and water that has a certain density that reaches the ocean surface in the Southern Ocean has a density that is equivalent to water that is 2,000 or 3,000 meters below the ocean surface, 1,000 kilometers further north. So there's a really direct pathway from the ocean surface into the mid-depth ocean in the Southern Ocean. That pathway isn't as clear in other parts, in the northern hemisphere, and it's not at all available in the tropics. So you're asking about salinity. I carefully avoided mentioning salinity because although you're right that there was an intent to measure salinity, in fact, in the 1990s, we were still learning how to measure salinity from floats. And the salinities are, maybe I'm not supposed to say this in public, but they were not actually usable for the 1990s. And suddenly, in about 2002, there was a big breakthrough. You know, 1 week I talked to the engineers, and they said, maybe in our lifetimes we'll learn how to measure salinity properly. And about a month later, they were doing it. So there was in the data from the 1990s don't have reliable salinities, and there's not an easy way to correct them. It is true, we now get good salinities from the profiling floats, we're getting good salinities from other sources, and the evidence shows, if I can find find a Southern Ocean plot. The evidence does show evidence for freshening right around Antarctica. That's not surprising. We've seen a lot of ice melt, so that's put a lot of fresh water into the ocean. And that's really the predominant effect that people have observed in the repeat measurements of this region.
Wonderful. Well, thank you very, very much, Sarah.
Thanks.